Alrighty, hi folks, I'm Vanessa Sochat. I am a principal computer scientist at Lawrence Livermore National Laboratory, and today I'm here to tell you about converged computing and agentic workflows, actually beyond Flux, although Flux is a part of that. Let's get started. So, we are in the post-exascale era. What does that mean? It means that our workflows are demanding more orchestration, automation, and different infrastructure. So perhaps the best way to think about this might be to look at where we've come from and look at where we're going. So who recognizes this? Raise your hand. Yes, this is bread and butter HPC. This is a Slurm batch script. So what do we have here? Well, we're telling the scheduler exactly the resources that we need, the cores, the number of nodes, the actual down to the topology. We also are asking for something that is static. Our MPI job is not going to grow and shrink over time. We also are setting a maximum runtime. It's not going to go over 48 hours. We're telling the scheduler exactly where our software is, down to the MPI library, the networking, everything. We are also the experts at optimizing our application. This means environment variables and flags. And so we can kind of summarize this. It's monolithic, it's batch, it's static. It is not discoverable. It is traditional HPC. However, this begs the question, what does the future look like? So this is a talk by Andre Caparthe from last year. In this talk, he talked about software 1.0, 2.0, and 3.0. And specifically, software 3.0 is conversational. So what does that mean for our workflows? Well, it means they might look like this. Hey, agent, I need you to run lamps for me. And I need it done by Friday. Get to it. And so the question becomes, how are we going to get there? So at the lab, we've been working on an initiative called Converged Computing for many years. We have a strong opinion that actually the bridge from traditional HPC to what we might call agentic science is converged computing. So why is that? Converged computing is the best of both worlds between HPC and what we might consider cloud native. This means that we want modularity, automation, declarative management, but we also want to keep our performance, our topology, our fine-grained scheduling algorithms. So if you can imagine taking those two things, slamming them together, the thing in the middle that you get is converged computing. And so if we kind of map converged computing into this space, what do we see? Well, we have coupled AI ML with simulation. We have dynamism, elastic. Our jobs are growing and shrinking over time. We also have agentic discoverable environments. No more hard coding stuff. Who wants to keep hard coding stuff forever? I don't. And if you're kind of astute, you may realize that a lot of the above is driven by your workload manager. For example, Flux Kubernetes. Alrighty, so we've been doing converged computing for a while. Let me give you a sense of some of the projects and how they've changed. So back in 2021, we worked on Fluence. This was a custom scheduler plugin in Kubernetes. This means we took FluxSched, we plugged it into the custom scheduler framework. In 2022, we moved to the Flux operator. This was deploying an entire Kubernetes cluster into Kubernetes. In 2023, we kind of flipped that paradigm and we said, let's actually bring Kubernetes to be running under a batch job. This was user space Kubernetes, the bare metal bros. In 2024, with resource contention, we said, oh my goodness, we are not ready for this change. Let's figure out all these different cloud environments. We did a large cross-cloud performance study across clouds, 14 environments, up to 256 GPUs, over 28,000 cores to figure out what was best for what. And in 2025, we took a traditional HPC workload, Mumi, and we mapped it into Kubernetes, and we showed improvements with cost and performance. And I apologize, the mask is a little bit hard to talk in. Alrighty, so how has our thinking changed based on converged computing? Well, it's gotten larger. Now convergence is an entire vision for an HPC center. It's much bigger. And so, to be clear, our initial thinking on converged computing was very small scoped projects. We were basically thinking about features, putting in one of these two environments. Now we're thinking about the whole tuna fish sandwich, the entire HPC center. And so in 2025, we did our first agentic study. We used Gemini. We deployed HPC applications in the cloud, totally agentically orchestrated. I'm going to talk about that. If you haven't been hiding under a rock, it's totally okay if you have, by the way. You'll notice that there also are national initiatives for this kind of thing. The Genesis mission, and that includes the American Science Cloud. At the lab, we also have FGHPCC. So what the heck am I talking about with this agentic science thing? Let's talk about what that means. Let me first tell you the story of how my thinking changed. So at the time in 2024, we were doing some transformational work, pretty simple, to convert batch directives and specifications from one format into another, Slurm to Flux. At the same time, I was using Gemini for really dumb stuff, debugging. And I was like, Gemini, can you do this? And what you're about to see is the result of what happened. Basically, this captures the moment that my thinking about LLMs transitioned from extreme skepticism to, holy cow, this is the future, this is awesome, let's move forward. So I realized that we needed to think bigger. Doing one job specification transformation was not enough. Let's ask Gemini to do the entire scaling study. And so what did that mean? It meant to build a container, deploy it to Kubernetes, optimize it, and then actually do the scaling study. And so we did that. It worked amazingly well. We wrote this white paper. And one thing we really learned, and probably many of you in this room have also learned, is that this kind of work is a balance between autonomy and control. And we'll talk more about this. You generally want to be somewhere in the center. So what did this mean for our study? Well, we actually used our own state machine framework. We didn't use AutoGen or LangChain because we wanted transparency. And so basically the combination of these components forms an agentic team. So that means that we start with a YAML plan. The plan is given to a manager. The manager can actually orchestrate different expert agents. For example, a deploy agent that has a helper agent. And then the scaling agent is the one that makes the decisions about the scaling. And then the optimization agent is the one that does the optimization. And then also some of our helper agents, like the result parser and the debugger agent, they can actually be human assisted. So for example, it would be a human that approves a regular expression to parse a result. Here's an example of some of our results. It did immensely well. So if you look at this plot, the orange line represents what would be ideal linear scaling. That would be the result at one node if we scaled it out. The blue line was the actual result, and so these results were immensely surprising. We did this for 6 HPC applications. So what did we learn? We learned that we learned a lot of things. You should check out the white paper. But we learned that transparency is important, and so this is why we didn't want to just jump into using AutoGen or LangChain. Prompting is really important, down to telling the agent what it's supposed to do, who it is. Capital letters, for example, that it's collaborative, for example, the human in the loop. That guardrails are really important. So for example, the scaling agent has an autoscaler that will prevent it from scaling to over 1,000 nodes, for example. Systems need to be self-healing. And then best practices aren't always best practices. So a really good example of this is with Docker multi-stage builds. We know that that's best practice, but when an agent does it, it's likely to screw it up. It's going to not copy over a library or an executable. So generally, you want to tell your agent not to do that. Alrighty, so how does this fit into a future vision for a center? Well, we wanted to redo our study, but using MCP, the Model Context Protocol. What is MCP? It is a standard for agents to use. It is a promise that when an agent makes a call to a server, for example, to list tools, it is going to get back a specific structure and format. And if you're kind of look at this and you squint a little bit, you're like, isn't that just like an API? What the heck is so special about this? And this was my reaction. Really, this was more of a cultural innovation than a technical innovation because of AI/ML. We finally agreed upon using a standard, which probably is harder of the two. So we decided to deploy based on use cases, and let me go through those. The first use case is the most obvious. It's I want to deploy functions that are specific for an application. For this use case, you want to deploy it under the context of a job. The second use case is maybe functions that might serve a center. So in this use case, you probably deploy it at your center level, your cluster level. It's likely multi-tenancy and managed by your HPC administrators. The third use case is the hardest. So this is like, I want an MCP server that's going to dispatch to different clusters. And so if you look at this, you realize that as you move up the levels, there's an increase in complexity and security. Because essentially on the outside, you have a web request coming in that needs to be mapped down to a user ID. It's not to say that we can choose one of these. All of these levels are important. Excuse me. Taking a breath. All of these levels are important, but we need to kind of work on all of them. Okay, so the next important piece is that components are pluggable and interchangeable. And I say this because I've seen a lot of demos come out of the lab where everything is hard-coded together, and if you wanted to change anything, it would be absolutely impossible. Toward this aim, we designed something called MCP server, a skeleton that where basically we can define a configuration file of functions and then run it like that, totally changeable. This is what it looks like running. And here, what are those functions? Well, here are the two libraries that we're maintaining. Flux MCP for the Flux functions, and HPC MCP for the grab bag of everything else. Okay, so how is it orchestrated? We have the server, we have the functions. Well, I want to argue to you today that an agentic framework is a design philosophy. On one side, you have the user goal. On the other side, you have your agentic framework, your LLM, so basically your brain. And then you have the tools and resource. And the way that you decide to have those things work together is the agentic framework. So we have our own design philosophy. We call it fractal A. How does it work? Well, you start with either a state machine plan or you start with a prompt. If you just start with a prompt, you're going to have a planner agent that makes you a state machine plan. And by the way, during this time, it can ask you questions. Once it comes up with a plan, a sub-agent then is deployed that starts working, starts discovering things in the environment, using the tools and resources to work toward the goal. And then, of course, because this is a state machine, that means there's rules for transitions, there's things to determine success and failure. And very importantly, you should annotate the functions on your server, the inputs, the outputs, and the doc strings so that your agents know what they do. So here's an example asking to deploy a Hello World job in Kubernetes. This is what it might look like. Okay, here's the user scientist. Here's what the server might look like. That planner agent takes it, makes the task. So notice how it's taken the simple prompt and expanded it out to include up to having the actual YAML manifest for the sub-agent expert. And then the sub-agent expert works on the task. And so here's for what this specific task that wound up looking like. Discovered the kube config, it created it, it then looked at the manifest, and eventually it got to the hello world. It worked very well. And so we used 3 agents in this specific plan. Here's just an example of what some of the fractal A interactions look like. Here's what our initial study looked like, written as a very pedantic plan to translate a job specification. Here's a harder example, asking it to discover software installed to SPAC and then basically to run it and parse the log. For those that use SPAC, you know that's hard because you have to source the SPAC environment and all this other stuff. By the way, the agents themselves are modular. You can add them on the fly to a server. And if you want to see more on this, come to our tutorial on Wednesday. We're going to be doing live stuff, which I'm sure will go great. All right, so next steps for fractal A work, we're going to be improving the MCP server. We're going to try to reproduce our scaling study using this new software and kind of just explore algorithms for multi-scheduling. Here's an example of how we're working on the MCP server to actually support kind of a hierarchy, because we expect that there's going to be MCP servers that deployed at different levels. It can serve as a hub or a worker, both or neither. And here's a really hard question. Are we ready for this change? The answer is like, maybe, I'm not really sure. So this is a cultural question. So are we ready from a staffing perspective? I want to quickly show you some of the requirements that we need. So first of all, asynchronous programming, Python, async IO, we hate it, but we can do it, that's fine. Event-driven architectures, so no long scripts, no polling. If you've ever done web development, you're probably just familiar with MVC, you're one step ahead of the game. Modern APIs, persistent service management, web security. And the TLDR here is that HPC really needs to become more cloud-like to use the latest technologies and stay relevant. So, strategies for getting started, if you haven't, actually I'm sure everyone in this room has. Start with a basic idea, like try to deploy an MCP server under a job. Does it work? Talk to your users. What do they actually want to do? Try out user space Kubernetes. Think of a long-term plan for your center, not just kind of a quick one-off thing. And here is what our team is actively working on. I think I already said a lot. I think the biggest thing here that's interesting is that we have integration added in Kubeflow for Flux. The rest, I think I've talked about already. Alrighty, so in conclusion, the HPC Center of the Future is built upon convergence, modularity, and agency. There's a lot of these things I have talked about. We need a hierarchical resource orchestration. Roles are changing. Be open to changing roles. You know, don't be afraid that AI is coming to take my job. And this HPC Center of the Future is not just a center for running jobs. It is a proactive, autonomous platform that accelerates science. Alrighty, that was really hard. Thank you for being patient with me. Any questions? Yeah, I think you can come up to the microphone here. If you want to, I guess you don't have to. See right up here?
Oh wow, this thing's tall. Okay, I was just like, I don't know. This was cool. Thanks for giving this talk. You had a slide about your MCP tools. If we could like look at that really quick. Yeah. Oh, I think this one. That's right.
Okay.
So I was curious about your HPC MCP one because I was in particular interested, how are you guys navigating like security on that? You know, if you have tools designed to maybe bring up logs within an HPC system, or like maybe you want to know models or hardware, you know, specifically what maybe the cluster has. Could you please elaborate on what you guys are?
Yeah, sure.
Yeah.
So both of these libraries here, I'll first say they're just provisioning the tools.
Okay.
So they're not actually providing any kind of a server. And it's actually the server piece that is going to implement any kind of security when it comes to the request itself. But you're asking a good question about the security of the function. So for example, in HPC MCP, there's functions for Docker, Kubernetes, file system, Git, deployment, SPAC, it's like a potpourri of things. And so in those functions, for example, if someone does a read of the file system and they're allowed to read a file that they shouldn't be reading, like what's controlling that? And the answer is it's really up to the deployer to basically control how that is orchestrated. So for example, for that particular function, when it's deployed, it is the deployer that decides the scope of access that they're allowed to get. So for an agent, you probably want to create a sandbox for it, and you don't want to give it access to your home directory with all of your little secrets. And you specifically asked about kind of discovery, right? You asked about discovery of software or hardware. We don't currently have Actually, so in these tools, we don't currently have discovery, but in the MCP server, it has a particular get status function where it actually is going to discover hardware, software, and that kind of thing. And that explicitly, right now, the way I'm designing it is that nothing that will get shown would be confiscating or security, high risk information. But if it comes to the case where a cluster has to expose that kind of information, then it would be up to the MCP server to have those kind of auth-Z kind of handshakes between the client and the requester to make sure that the person that's asking is allowed to get that particular information. So it's not really any different from traditional auth-Z at the end of the day, because the requests are of that format.
Cool, thank you.
Sure.
So my question is around, how do you handle error scenarios? What is the feedback loop?
Oh
the
gosh,
agent
that is a
workflows,
good.
if there is any errors during this deployment?
Yeah, that is a really good question. So let me tell you, the first iteration that I did of this particular library, me as a human, I was watching a lot. And so what I would tend to see are patterns where the agent would always almost go wrong, but then it would just go off the rails, almost into another, a minimum that was not optimal, and then it would be terrible. So the first kind of high level thing you can do for a specific scope use case is to basically understand those kind of scenarios, and then make sure that you put in prompts or kind of checks so that the agent never or is unlikely to get to that. Now, of course, you can't guarantee that, right? And so generally speaking, what then we added is you'll have a maximum number of kind of retries until you go back, and then you go back to a previous state. You either restore a previous state or you hand execution back to the manager. And then it becomes a debugging issue. There's actually a separate debug agent that does not store memory. And then you tell the debug agent, this is the current state, this is what's going on, what do you recommend we do next? And the debug agent also has the option to get feedback from a human. So it's really a bunch of checks and balances, making sure that you have a maximum number of retries kind of thing, making sure a human's in the loop. I'm very pedantic about running these studies, so I am usually watching them, trying to understand what's going on. And then, but you're right, that is really hard, because the second you change the context and you're doing something new, totally new problems, right?
No, I understand. This is basically your flow of logic within your agent deployment, right? But what if you're deploying it in a Kubernetes cluster, and if there is a network failure, for example?
Oh, right. So you're talking about if I were to submit a job and there's a network failure.
Yeah, exactly.
Right. So you would need a way to basically ensure that that information gets back to a, I wanted to say the central scheduler, but more likely you have a raft framework where there's a leader at the moment.
Does it undo whatever it did until that point?
So we have not built that yet. We're talking hypothetically here. You would want that message to get back, and then to be able to understand the work and find the other clusters that are suitable for it.
Okay.
But that's a much larger problem when you're talking about scheduling, and that is not what I was talking about today.
Okay. Thank you.
Sure.
Vanessa was very efficient in her presentation, so we still have a few more minutes for questions time before.
Yeah, let's get some more questions.
So, somewhat related question: how do you handle provenance and reproducibility when you're
provenance and reproducibility?
Yeah.
Yeah. So when you're talking about reproducibility, so I come from container land, so that's a very specific word. I don't think it's likely that with an LLM that you're going to ever get the exact same results again. So I don't know how to control that. I'm sure there's research going on. Now, with respect to provenance, that's a different thing. So with respect to provenance, at least what this software is doing now is that for every step, every prompt, basically any kind of interaction that happens, we are saving that metadata. And so the MCP server has a database backend interface where you choose your interface. It could be memory if you don't want to save anything. It could be the file system, or it could be an actual database. And we save everything there. And that's really important because generally speaking, after, we want to come back and look at things, plot them, see where we screwed up and we need to try again, right?
Yeah.
And I think that's really the best you can do. Reproducibility, when you're talking about LLMs, that is a hard question I don't know the answer to.
Okay, thanks.
Awesome talk. So I was curious what y'all are doing in the way of sandboxing. We have a similar-ish project at Lionel called Ursa, and I think currently we have support for like either Charlie Cloud or Docker as far as sandboxing options of containers. Have you looked at that?
So we haven't specifically, a sandbox can technically also be, a bad sandbox can technically just be a scoped access to a particular like temporary directory.
Yeah.
I guess I was going to say my preference would be for Singularity with a bind mount, but my lab doesn't do Singularity anymore because there was a security thing. Yeah. So I guess my options now are just Podman.
Right.
So maybe Podman. I think the challenges with sandboxing is just how allergic HPC systems are to generally rootful container technologies.
Yeah.
So I would say that is a center-specific question. The container technology that your center has the most experience with is probably going to be the option that
Yeah,
you
that's why
want
we're
to
using
go
Charlie
with.
Cloud. Same deal.
Yeah. Cool.
Thanks.
Okay, we might have chance for one more question, and then we'll switch over. Okay, then I think we'll.
Yeah, just thank you, everyone. I have not given a talk in public in 9 years, and this is my first, and I'm also wearing a mask that is actually kind of hard to breathe in, if you couldn't tell. So I really appreciate your patience and all that.